So now let's analyze the forces in the truss. And remember, at each node, the forces are going to be aligned with the direction of the member. So that means, just like with a cable structure, at each location, we're just going to draw a triangle, or in this case, a polygon, because often we'll have four members coming together of closed vectors that have to close on themselves. So we're going to follow much the same methodology as before. So first I have to draw my reaction forces. So in this case, since I have a single load in the middle, P, by symmetry, that load is going to split evenly at the two ends. Now we have to label the regions. And it's a little bit different than in the cable structures because we have both exterior and interior regions. So the way we're going to do it is we're going to label the regions between the external forces with letters, just like before. So I'm going to go around A, B, C, and now this whole region above is A, because there's no forces there. The regions in the interior of the structure, I'm going to use numbers 1, 2, 3, 4, 5, 6, and 7. Now, just like in the cable structure, the first thing we're going to do is draw our vertical load line. So I'm going to take a line here, let me line it up. So I'm going to take a line here, and I'm going to use 2 units as my load P. So let me mark off 2 inches here. Okay, so there's my downward load line. So going from region B to C is 2 inches, so that's my load P. Going from C to A, it's P over 2, but upwards, so A is right here in the middle. And then going from A to B is another half unit of P going upwards. So that's my load line. Now we just have to go and draw the interior forces. So let's see. So let's start here. So this member here is B to 1. So there's going to be a vector coming out of B, which is going to be horizontal. So let me draw a line, horizontal line coming out of B. Now intersecting that, A to 1 is going to be at this 45-degree angle. So let me line up with my structure here. Let me draw a line here, and where those two intersect is going to be point 1. Now we can figure out if the members are in tension and compression by kind of thinking about the directions of the vector as we go. So A to B is this one here, which points upward, which means 1 to A, better point downwards, which means B to 1, better point that way. So those are the forces on that joint, and we can figure out whether each member is in tension or compression as we go. And also as we go, if we want to know what the loads are, we can measure these distances. So right here, this gives me 1 inch from B to 1, meaning that the load in this member is P over 2. And this gives me almost 1.5 inches. And if we work that out, that will be the result we found before, P over 2 root 2. Now we can continue kind of quickly just following this same methodology, and all I have to do is locate points 2, 3, 4, 5, 6, and 7. So 1 to 2 is going to follow also on this 45-degree line. So I'm going to have another line going like this. 2 to A is going to be a horizontal line. So I just come here and I create a horizontal line coming out of A. Now there's point 2. So that's the force triangle between points A, 1, and 2, which is this node right up here. If I want to find the load in this member right here, again, all I do is measure the length of that line. But let's kind of proceed quickly now. So 2 to 3 is going to be angled at 45 degrees. So point 3 is going to be somewhere here. 3 to B is going to be extending along this horizontal line. So there's point 3. Now we can see B to 3 quite a bit longer than B to 1. So we kind of see that adding up increments just like we saw in the analysis. So this length is P over 2, P over 2 to the midway there, P over 2. So this one's going to be 3P over 2. So we can just measure our lines as we go. 3 to 4 is going to be located along this 45-degree line. So I'm going to move that point there. 4 to A is going to be along our horizontal line. And there's point 4. Now, the other half of the truss, because now we're at the midway point, by symmetry, should look like this same thing, but rotated over. But let's actually confirm that that's true. So, 4 to 5 is going to go this way. So 4 to 5 better be going that direction. 5 to C better be a horizontal line coming out of C. So where those 2 points intersect is point 5. Now if I've done this carefully, points 5 and 3 should be pretty symmetric, which they are, which means the load in this member and this member are the same. All right, 5 to 6 is going to be along a 45-degree line. And again, we've done this pretty good because it intersects right back here. So this is not only point 2, but point 6. Point 7 should be symmetric with point 1. So that will be point 7. And finally, this last point here, 7 to A, is going to correspond. Oops, I've kind of run out of room on my table here, but is going to correspond with that line there. So there's my force polygon. We can see by far that A to 4, this one is going to have the highest load, and we see the same thing that we saw when we did the analysis, which is all of these diagonal members right here are all the same length. So this gives us a very quick methodology to analyze the forces in these truss structures, and all we have to do is construct this diagram, be a little bit careful about our notation, and then go and measure the length of the line when we're done. So let's try a variation on that last example. So in this case, we're going to have 3 units of P pulling down at each node. So this would be more realistic for a bridge because the load is more uniform across rather than a point load at the center. Now to support this, we need to have a reaction force at each end. Since there's 3 units of load pulling down, that means at each end we need 1.5 units of load pushing back up. The next thing we need to do is label our spaces. So just like before, I'm going to label the exterior spaces between our forces with letters. And I'm going to label the interior spaces with numbers. Perfect. Now the next thing I need to do is draw my load line. So my load line should be vertical. And so let me try to align my ruler on the structure, get a nice vertical line here, and I'm going to make it 3 units because I have 3 units of load downwards. So I'm going to make my unit load 1 inch. So B to C is one load, C to D is the other load, D to E is the third load. Now going E to A, I go up and I go exactly half. So I go right to the midpoint, point A. Perfect. All right, now all I need to do is exactly like we did before, go to each member and draw the forces. So B to 1 needs to be a horizontal force. So I need a vector, a horizontal vector attaching to point B, going somewhere out here to point 1. 1 to A is going to be this 45-degree line, so I'm going to line my vector up there, my ruler up there, come out here, and where those 2 points intersect is going to be point 1. Now again, I can take my ruler here and I can measure the line. So here B to 1, and it looks like I'm getting about 1.5 inches, so 1.5 P. So again, as we go, we can measure the length of the line. We can also work out what each member is in terms of tension and compression. But let's just work the structure. So 0.2 to 1. So 1 needs to connect to 0.2, do a 45-degree line like that. 2 needs to also connect to point A through a horizontal line. So coming out of our midpoint A, those two lines intersect, point 2. Now we just continue. 2 to 3. 3 to C now. So now this comes out of point C. So now we see a little bit of difference than what we had before, because now we're coming here. So where those two lines intersect, that's going to be point 3. Now you can see the advantage to doing this in pencil, because it allows you to, I could kind of erase where I've overshot. I'm doing this in pen so it shows up nicely for you. Now we need to locate point 4. So point 4 is going to be the 45-degree line coming out of point 3. There we go. 4 to A is going to be a horizontal line coming out of A. Perfect. And again, all we have to do is measure the length of the line, and that gives us the load in each member. Now if we continue, we should be able to finish this structure by symmetry, but let's just kind of do it anyway. So 4 to 5. So 5 should look very much like 3. 5 should be connected to D by a horizontal line, so let's find point D. Oops, ruler slipped there, so let me just do that again. So there's point 5 and 3, which looks symmetric. That means 6 and 2 should be nice and symmetric. You see I moved a little fast there, so I'm a tad off, but I can tell by symmetry those points should line up. 7 needs to connect to point 6, so it's going to look very similar to point 1. So 7 should connect to point 6 by a 45-degree line. Finally, E to 7 should be a horizontal line. And there it is. So there's our force, and there's our form. And again, all we have to do is take our ruler and measure the length of any line, and that gives us the force in each member of the truss. Okay, let's do the next example, which is slightly different geometry, but kind of same idea. So we have a different arrangement of the members of the truss. We have a uniform load P all along. In this case, we have 1, 2, 3, 4, 5, 6, 7 units going downwards, which means my two reactions need to be 3.5 units going upwards. So we're going to label the regions between the forces with letters A, B, C, D, E, F, G, H, and I. 1, 2, 3. Wow, so there's a lot of members in this one. This time, since it's symmetric, I'll only go up to the midpoint and then we'll stop. So I'm going to need 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 regions here, but that's 7 loads. So I'm going to need 7 units of load going downwards. So let's line up with our structure here. I'm going to take this as close to the edge of the screen as I can. And let's go downwards from here. So there's 1, 2, 3, 4, 5, 6, 7. And now we see we're going a little bit off the screen, but it doesn't matter because we're only going to go up to kind of the halfway point anyway. So this will be point P, B, C, H, and I. All right. And again, just like before, we're just going to work our way. So I'm going to start at this end. So point B coming out as a line like that. But we've forgotten to locate point A. So point A, remember, is going to be bisecting this long load line because from B to A, it's going to be 3.5 units, right? So it should be right here between points E and F, right in the symmetry. So that's point A. All right, So in this structure, we've obviously drawn the line coming out of B to be a little bit too short. So there we go, that looks better. And there we've located now point 1. So now we can see the lines are quite a bit longer, but that's just because now we have 7 units of load going down. And again, now we just kind of work our way through. So 1 to 2 is going to be a vertical line here. 2 to A is going to be a horizontal line. Now we see we didn't quite make this one long enough, so let's try that again. A little wiggly ruler there, but that's okay. Perfect. So there's point 2. 2 to 3 is going to be at a 45-degree line, and it's going to have to come up and connect with point C. So 45 degrees here, point C here. Now we've got point 3. Perfect. 3 to 4, vertical line. 4 to A can be a horizontal line. So this line out of A is just going to kind of continue. So that's 4. So 3 to 4, this line here. A to 4, this one here. 4 to 5, another 45-degree line. 5 to D, another horizontal line. So I think you should be getting the picture now. This is just, we're just going to kind of keep continuing the same thing. So let's go 5 to 6, another vertical line. There's point 6. 6 to 7, another 45-degree line. 7 to E, another horizontal line coming out of E. And there we got it. So I'm just going to go up to there because the rest is going to be the same by symmetry. So that's 0.7. And again, all we have to do is anytime we want to know the load of any member, we just come here. This is C to 3. So this one right here, we measure the length of the line and we've got the load. Okay, our final example will be a cantilever beam. So here we have a truss structure, we have a point load P at the end, we have this anchor to a wall here, and we have an anchor to a wall with rolly supports here. So what that means is that this has to be exerting a reaction force P here. And as we saw in a prior video, if I sum the moments around this point here, I have P pulling down. That contributes no moment. So this needs to be anchored to a wall with a force great enough to kind of counterbalance that moment so that it doesn't rotate about that point. So here we have P acting 1, 2, 3, 4, 5 units down. In here we have 1 unit up because this is a perfect square. So that reaction force here is 5P. So what that means now is that this needs to be pushing with 5P in that direction. Okay, so now let's start to analyze the forces. Let's draw our letters between our regions. So A to B will pass through that external force. B to C will pass through that external force. C to D will pass through that external force, and D to A through that one. Our interior regions will be 1, 2, 3, 4, 5, 6, 8, and 9. Now let's draw our load line. So I'm going to line up my vertical member here, and you'll see why I'm drawing it here in just a second, but I'm going to draw my load line here in this direction because now the structure is going to move out this way. So A to B, that's point A, that's point B. B to C is going to be a horizontal line of 5 units. So let's line that up here. So that's going to be point C. So A to B is down, C to D is out. B to C is out, C to D is back, so this is also point D. D to A is up. Now we just need to draw our loads. So A connects to point 1 through this horizontal member. So 1 is going to lie along this point somewhere. B to 1 is going to lie along this 45-degree line. So where those two lines intersect will be point 1. So there's point 1. And again, I measure the length of the lines, and I've got the loads. Now we can kind of see by analogy here, A connects to point 3, 5, 7, and 9 by horizontal lines. So I think what I can guess is that this is going to go out further. Okay, 1 to 2, vertical line. So there's point 2. 2 to 3, 45-degree line. 3 to A, horizontal line. 3 to 4, vertical. So there's point 4. 4 to 5. So now in this case, and then 5 to A is this line right here. 5 to 6 goes down. 6 to 7 goes at my 45-degree angle. 7 to 8 there's point 8, and then there's point 9, and then 9 to A is this here, so that is just I drew the line too long. So we see that 9 to A is the force here. We measure that and we see it's 5, so this would be 5p. A to 7, we measure that, 4p. A to 5, 3p, 2p, and 1p. So again, just by measuring the length of the lines, we get the loads in the members. Down here at the bottom, B to 8, 4p, 3p, 2p, 1p. And we can just see that from measuring the length of the lines. And again, if we work out tension and compression, we can do that as well. But what we'll find is that this wants to bend downwards, and so all of these upper members will be in tension, and all these lower members will be in compression. So which members are in tension and compression we'll talk about a little more in a subsequent video. In this one, what I just want to do is go through several examples showing you how to compute the force diagrams from the form. So again, it's hard to just watch me do this. You'll have to try a few examples yourself, but once you get the hang of it, it's super easy.